Okay, so my name is Rich Graham, and what I'm going to talk about today are some of the challenges that we face, that all of us face, as we're trying to increase the scale at which we run our applications, and specifically the focus that I'll focus on issues revolving around how this affects the network, and so obviously. Increasing the scale at which we run brings quite a few challenges. I hear feedback. I don't know if.
Yeah, we don't hear it.
Oh, okay.
It's not a problem for us.
Okay.
Good luck.
Quite a few challenges in terms of being able to use these very large scale systems efficiently. And I've listed here briefly some of the challenges that we face in terms of scalability and
lower. Yeah, there's
a hot mic.
Yeah.
And then how this reflects itself in terms of potential solutions to these problems. The number of functional units that the applications will need to use is expected to grow and be extremely large. People talk about order 10 million. So once we may have thought that was fictional, but even today people are using 1.5 million cores, for example, in the system at Livermore. So we're in the realm where it's only an increase in terms of an order of magnitude of number of compute resources that are necessary to reach these sort of goals. And how this reflects itself in terms of solutions, and specifically in terms of APIs or standards such as MPI. SHMEM is becoming a little more important now. Or is the ability needing to be able to scale the communication capabilities to large scale. That affects point-to-point communication and collective communication. These are the predominant ones that are used by applications today. The size of functional units, the size of hosts, the number of functional units per host is increasing. At one point, folks thought that maybe we're talking about order of 500 or so compute elements, and today's GPUs have several thousand. And so what this really means in terms of the ability of the network to support that, you have to have a very scalable architecture so that you can handle a lot of sources of data in an efficient way, and to be able to drive the network, to be able to provide the applications the data that it needs over the network. Memory hierarchies are getting deeper. Trying to take advantages as the packaging on die packaging increases, the memory in effect gets further away from those processors. So need to take into account as much as possible these sort of hierarchies in memory. And take advantage of them in the implementation. So cache-aware network access is one way. When you talk about developing communication capabilities, you also take these sort of topologies, these sort of hierarchies, in communication cost into account. Smaller amount of memory per functional unit. So this is quite a challenge in terms of communication libraries, because you need to be able to support communication for much larger number of endpoints, but you don't have as much memory to do that with, and so you have to come up with techniques that reduce the amount of memory required to manage communication on such large scale. Functional unit heterogeneity. The whole issue of handling different endianness different endianness or different just data representations on the node, and this is becoming more common as GPUs and other accelerators start showing up on the network. need to plan for failure, minimize data movement, and really focus on making independent progress on the network. This is an important piece if one wants to get to high efficiencies or to get to usable, reasonable efficiencies on very, very large systems. Prefer not to use the same resources that you use for computation to progress communication, because that just hinders overall application performance. And then power, as everyone knows, is a major issue. So working on reducing power is really important. So these are sort of the when we think about how to continue and change the network over time, these are really the sort of things that one looks at. The items that are listed on the on your right side of this table here, in terms of these are the sort of things that need to be addressed by a network design moving forward. So I sort of alluded to these already. You know, from the perspective of building communication libraries, really very important to provide truly asynchronous communication capabilities. You know, this reflects itself in all types of communication types that are being supported. The goal here really is to be able to allow the application or give the application the opportunity to make as much use as possible of the compute resource for doing the compute portion of their application, while letting any sort of network, as much of the network activity as possible, happen in parallel and behind the scenes, and not consume the same resources and not compete with the compute portion of the application for the same resources. Really want truly one-sided remote progress. So need the hardware to support these sort of things. Obviously, as you grow in scale, issues around system noise become more and more important. And so in terms of a communication library, you really want to use strategies in implementing that allow you to reduce the effect of system noise on a running application. Then topology awareness is something that lets you really accelerate communication if done right. So I'll sort of set the stage. I set the stage with some of the challenges facing us, and what I'll switch to now are some of the ways that at Mellanox we were looking to address these challenges over time. And so first of all, from a solutions perspective, we focus really on using standards. So you have interoperability with other hardware providers, but also over time, so that you can evolve your systems over time and still have interoperability between components. So this comes both within using or implementing standardized protocols at the hardware level, you know, where we implement the hardware, the InfiniBand standard, but also in terms of the associated communication libraries that we develop to use these capabilities. We also support standards, and our focus these days is primarily on MPI and SHMEM, with MPI being by far the largest API in use by applications today. But there seems to be some growing interest also in using an explicit SHMEM interface, at least in some communities. So these are really the focus of our solution in hardware and software. And so from a software perspective, the intent is really to allow applications to build on top of standard interfaces and let the lower levels deal with changes in hardware over time. So in terms of solution, over time we've been making steady progress in terms of improving, basic speeds and feeds, memory bandwidths, and latencies. Today we're at the stage where we've started to introduce 100 gigabit per second technologies, or our EDR technologies, and this will continue moving forward in a very very methodical way. So what I want to talk about now is give a brief overview of our current host channel adapter, ConnectIB. Even though this is our current product, it's one that's a few years old, but it's very relevant in terms of moving forward with from an architectural perspective, because from an architectural perspective it forms the basis for future HCAs. So it's the seventh generation of adapters from Mellanox. It's the first adapter that actually supports 100 gigabit per second throughput on the card. And I need to be clear here, this is not single stream, this is a dual port FDR 56 gigabit per second adapter, but it's been demonstrated to work in practice with MPIs that can stripe, being able to drive an application level thing, 100 gigabit per second. So this really sets us up very nicely to be able to transition to the next step in technology, where in a single stream we can support this sort of bandwidth. Drive very high message rates, 137 million messages per second. And the message rate becomes important as you increase the number of cores, because as you have the number of cores per host, as you have a single host channel adapter that tries to service all sources of data within a given host, you have to be able to support higher message rates if you want to be able to drive the network at the speed, at full network speed, and more important to that, to serve the data to the various sources or destinations of data on the host. So that's why the very high message rate is important, and over time this message rate will continue to increase to meet the larger demand of the growing number of endpoints on a given host. Probably one of the more interesting new features on this card is a new transport called dynamically connected transport that was designed in the first place to deal with scalability. And I have some slides later on that I'll talk about here. So we really have, with this HCA, started to make some very big strides towards, first of all, with an architecture that will let us scale to large scale, but also from an absolute performance perspective and a feature perspective, give us capabilities that are necessary to go to the next level in terms of support for communication. So just a few bits of information on performance data. We have some data from that was measured by DK Panda's group at Ohio State in terms of bandwidth with ConnectIB, and we see that they're able to come close to saturating the wire, get a bit over 100 gigabit per second unidirectional bandwidth, and about twice that on bidirectional bandwidth. So good characteristics, performance characteristics. As I said, we're at the stage where we're starting to enter our phase of supporting 100 gigabit per second compute capabilities. So this is from our perspective, we support a full ecosystem for communication. And so what that means is every piece that's involved in the process of getting data onto the network and pulling it off has to be moved from current FDR speeds to 100 gigabit per second speeds. And so back in March, we demonstrated the ability to transfer these at these sort of speeds at the 100 gigabit per second speed with several different technologies. The one that was most interesting at the time probably was silicon photonic capabilities that we provide, as well as VCSEL capabilities, and we also support the same sort of 100 gigabit per second on with copper. And so that piece now is that piece of the technology is now in place and working in production. At ISC in June, we announced our first switch, 100 gigabit per second switch, 36 port switch with under 130 nanosecond latency per port. The switch is a non-blocking switch, can drive bidirectional 100 gigabit per second, so it provides total throughput of 7.2 terabytes per second. It also adds the ability in hardware supporting an InfiniBand router, which lets you do two things. It lets you, one, isolate traffic, have isolated domains within your network, and with very fast transfer of data between domains, done at the hardware level, very low latency penalty for doing that. And so it lets you have a subnet that's your compute node, another subnet that might be your storage node, and very, very rapid communication, and very high bandwidth actually communication between them, because you can have many, many routers between subnets. The other thing it lets you do, if you want to build systems that are larger than what you can support with the local ID space, the lid space today, because the latency here is so low, you can do that also with the InfiniBand router. And so you can build much larger systems if you want to with this technology. The topologies that are supported by this switch is agnostic to particular topologies. You can build basically any topology you want with it. No restrictions in terms of what you can do, but we have optimized support for several topologies. That is, we build optimized routing for several topologies, specifically fat, tree, torus, and the new topology that we're supporting now is a Dragonfly topology. We call it Dragonfly Plus because of the nature of the subgroups. I think I have a slide about it a little later on. So in terms of scalability, in terms of performance, in Mellanox we invest quite a few resources to build software libraries that can take good use of the hardware capabilities that we provide. So there's a lot of work that goes on in terms of providing optimized collective communications for both MPI and SHMEM and UPC. So these algorithms are topology aware. That is, they take into account differences in latencies and bandwidth capabilities and the like in the network, and that you build very efficient collective communication capabilities. They take advantage of hardware multicasts where appropriate, to send data out in order one time, independent of the size of the system, or almost independent of the size of the system. It supports offloading of collectives to the HCA, to the host channel adapter. I'll talk about this a bit later on. The big advantage here is being able to basically avoid system activity or system noise, and so really help in terms of scalability of applications, and the algorithms that we use are scalable algorithms. So we implement well-known algorithms, but we also invent new algorithms to deal with issues of scale and the like. So I said I would talk a bit about dynamically connected transport. This is a new transport that was introduced with ConnectIB. It's released at general availability level now within Mellanox SOFED, so it's available for use by applications. Really, the main goal of this transport is to have a transport that scales well with the size of the system. In this particular case, the transport itself is the amount of resources required by this transport is essentially independent of, is essentially independent of the size of the system, which is what one really wants. So a few things to note about this transport. It's asymmetric. That is, in its definition, it has initiators that send data and have targets that are the target of data. And so a target cannot be a source of data, for example. The interesting thing about the initiator is a single initiator can send data to any target it wants to in the system. There's no notion at the user level of setting up connections up front. That data is sent basically on demand to any target. So it's very, very similar in terms of the way it sends data, the way the data patterns to unreliable datagram that many of you here may be familiar with if you've used InfiniBand in the past. Where it differs from unreliable datagram is one, this is a reliable transport, and so you don't have to build any software mechanisms to deal with unreliability. The second thing that it does, since it does have a reliability context, it also lets you use RDMA with this transport. So you can do any sort of the same sort of network operations that you can do with reliably connected transport with RC. You can do with DC. So RDMA write, RDMA read, atomic operations, and the like. Where it differs from UD is because it is a reliable protocol. There's a cost to reliability. That is, while in practice you can and people do send data to from a single source to different targets, because it has to guarantee reliability. There's a latency penalty between when one switches sending data to another target. That is, you have to make at the hardware level, one has to make sure that the data has been transferred reliably before it will change the destination to which it will send the data. And what that means from a library perspective is one has to take into account basically the fact that you have this latency penalty and use an appropriate number of initiators to hide that latency. That number is not very large. It's just several hundred, which is several hundred initiators to drive the network at full bandwidth for very small messages, 8-byte messages or something like that. And so from a resource perspective, this is not a limitation at all. The way this differs from RC, as I said, this has communication characteristics of RC. It's reliable, can support RDMA, but the way it's different from RC is that there's not a dedicated connection between two endpoints. So you can send the data and to any target you want, and underneath the covers, the hardware itself, much more efficiently than software can, worries about handles setting up the short-lived connections. So the reason this resource is independent, the amount of resources necessary to drive the network at full speed is independent of the system size, is because the characteristic of a single node. So a single node can only drive the network at a given speed. So for example, with ConnectIB, I just showed you that the hardware is not capable of sending more than 137 messages per microsecond. It's simply not possible, and it makes no difference how large the system is. The hardware is not capable of driving, both from a perspective of HCA as well as from a perspective of the CPU that's necessary to get the data onto the network. And so you have an upper limit that serves in terms of amount of traffic that can be generated, and since that's independent of the size of your system, the amount of resources that are necessary are independent of that. So if you think of a system that can drive messages at 150 million messages per second. You know, worst case scenario, round trip latency, say about 2 microseconds or something like that. So 2 times 150 or 300 initiators roughly is all that you need to be able to fully saturate, to drive the network at absolute top speed in terms of message rate, or in terms of amount of messages. And so you can't go above that. And as I said, from a resource perspective, the card is this is well within, well under the limits at which the card can support this transport efficiently. So as I said, this transport is usable today in our products, MXM specifically, which we use to support point-to-point communication. This is supported today, and it's a good transport to start experimenting with. So I've already talked about these points. So just a cartoon here in terms of resources. You know, if you're using RC, for example, because you want to use RDMA, atomics, or the like, the amount of connections you have is dense. Okay, of course, a lot of scientific applications have sparse communication properties, so they may not be as dense as this is. But in general, the amount of resources is large. But with dynamically connected transport, wondering if this animation is going to work. It's not working. Anyhow, there is animation where actually this changes, and the nice thing about it, about the change, application libraries don't have to guess here. I mean, that's one of the big challenges with writing communication libraries, is you really have to guess what, you know, there are always trade-offs in terms of algorithm implementation and the like, and you really have to guess in terms of what do you think is most effective most of the time, and hope that most of the users this serves most of the users. With dynamically connected transport, there's no guessing here. The hardware really does things based on the actual, supports communication based on the actual usage pattern of the application. And so it really removes the burden from a communication library development of trying to guess at a best strategy in terms of the trade-offs for implementing support for communications. In terms of topologies, as I said, we've in current technology, we support optimized routing for 3 topologies. One is the fat tree that probably most are aware of, and most have used. We also support mesh or 3D torus. And as I alluded to before, we've added support for a dragonfly type topology. And so dragonfly in general, for those of you that are not familiar with it, is in a dragonfly topology, you have islands localized islands within the network and that are fully interconnected, or that are interconnected in an all-to-all fashion. And so in our support for a dragonfly, our islands are based on a 2-level fat tree, and we do that really for 2 reasons. One, it gives us a very small latency penalty while being able to build fairly large subgroups. So going through this island through a subgroup, if you're going directly out, for example, you only have to pay a penalty for 2 traversing a router twice. If you have a 2D fat tree, for example, which Cray supports, you go through 3 most of the time, and so this was designed to reduce the number of hops. The other thing it lets us do, one of the challenges with routing is avoiding credit loops, and so with this very simple topology, all we need is two two levels, two virtual lanes to be able to deal with credit loops. And so what it means in effect is supporting this sort of topology. We can still leave 4 levels of quality of service from an application perspective for use. If you use something like the 2D butterfly, you have to use at least 3. And so on a system like ours where we have, in hardware we support 8 different virtual lanes, that means only 2 levels of quality of service. And so this gives us the ability to support quality of service better on our systems. As I said, the hardware itself is agnostic to topology. We've just optimized for these topologies. I've mentioned routers, so let me go on. Brian, how am I doing in time?
You've got 20 minutes.
Okay, thanks. Okay. So the next piece I want to talk about is the support for offloading communication, collective communication capabilities to the network. So this is capability that we've had in our hardware for several HCAs right now, and although the support in software has just been released within the last year. So I have a cartoon here to try and explain why this is relevant. You know, why someone should care if support for your collective communication happens on the CPU, happens on the network. Why does it make a difference? And so I have a diagram here of a very, very simple collective algorithm in which, you know, data. We have four processes participating in the collective communication, and the characteristic of the communication is data is funneled through process 0 and then funneled out to everyone else. So this can be used in a barrier. This can be used in reduction. There are multiple algorithms that might be built on top of something like this. And the relevant thing here is that. For example, the first step here, at process 0, you can't progress to the second step in the algorithm until you receive data from process 1. You know, process 2 here, for example, can't proceed until it receives data from 2, which can't proceed until it receives data from 3. And so the point of this is there's implicit coupling between processes in the communicator. And on your system or on any computer system, there's some sort of services that need to be provided for the application. You know, someone decides to do I/O, and so there's a system service that needs to deal with that, and the like. And so you have system activity periodically, which takes away time from the application. There's nothing negative here. We've written it and marked it in red because it impacts application, the running application, but it's an activity that has to happen. And what happens is when you have that activity, if it's not synchronous, well, if you have that activity, then it basically slows down at the rate at which the application progresses. And if it happens, here process 2, if the system activity happens before it gets to this stage in the collective communication, it's going to slow down process 0, and basically you have this coupling between all processes. So if system activity is not very tightly coordinated, then you get very, very bad scalability problems. And this is probably many of you are familiar with. There's a nice paper about this around 2002 or so that showed actually measured results from, at the time, Q at Los Alamos, where at scale, I think it was 5,000, 6,000 node system or so, the application performance slowed down by a factor of 2 because of these issues. And so system noise manifests itself in a very negative way in collective communication, which of course most high-performance scientific applications use because they needed algorithmically these sort of characteristics. So if you can move the processing, the progression of communication, of collective communication away from the CPU, and let the network do it, then you can avoid some of the effects of the system noise. So I have in a cartoon here, once you basically, let's say, program the card, it's not really programming the card, but once you hand off the collective communication to the network, any sort of system activity that happens afterwards doesn't affect that collective operation. And so being able to progress collective communication on the network has a big advantage in terms of being able to avoid some of the effects of system noise, which are very important, can be very pronounced as you increase the size of the system. And the other point I make here, I mean, this came in another context, but the other point we make here, if in addition to that, folks move to using, rather than blocking collective communications, if the algorithms, the applications can support that, then you reduce the penalty, then you provide a much better opportunity for overlapping communication and computation. So basically what you have to do is post your collective communication to the network, go off and do compute work, and when you want the data, when you want the result of the collective communication, you can basically come and check and see if it's ready and use it if it is. So if you can do this, support that sort of overlap, that's an additional advantage. And so those of you that use MPI are probably well aware that non-blocking collectives were actually voted into the standard maybe 4 years ago, but the standard itself was released 3.0 about 2 years ago. And so and all MPI implementations that I'm aware of today support non-blocking collectives. And so so what does this have to do with Mellanox HCAs? Mellanox supports a capability that's called Core Direct, and what Core Direct what Core Direct does is it really provides the primitives that are necessary to support collective, to offload collective communications to the network. And so if you remember the way we build our HCAs is all our queues, all our message queues are sitting on the card. So once someone offloads. Once someone posts a send, for example, or receive to the network, there's no more CPU activity necessary to progress those work requests. So to progress the sends or the receives, the atomic operations, and the like. And any of you that have done measurements and point-to-point communication on the cards to see how well you can overlap communication with computation, you see that's one thing. That's one of the things that our cards are very, very good at, is doing that. But with the initial implementation before Core Direct, all activity was any sort of synchronization that could happen or happened within the context of a single queue pair or and what that means is there was no mechanism for really coordinating data from multiple sources at the card level, which you need for collective communication. So with Core Direct, what was done was basically adding some very simple primitives, very simple new send work requests that let you do that coordination. So in addition to the ability to post a send, post a receive, post an atomic operation, RDMA read or write, this added the ability to say, wait here until some sort of communication on a different QP has ended. And so if you need, for example, if your collective communication had data coming in, say, from 2 different sources, if you had to wait on 2 sources of data before you could generate the data for the next step in the communication, this primitive lets you do that. So you can wait for data that's happening, for communication that's happening in a different communication context, and then progress within your QP. And there's another synchronization primitive that I won't get into detail right now. And so adding those very simple work requests in practice means that you can offload the entire collective communication to the network. You need to build a description of the collective communication locally. I have a picture here of what it looks like. It's basically a description of the communication pattern. Hand it to the card. Go on, and when you want to use the data, all you have to do is check and see if the operation is complete. Let me not go through. I have another example here for a very simple recursive doubling for process case. What setting up the collective communication would be like. So if you notice, for example, in the first step, conceptually, what happens in the first step of this recursive doubling algorithm, you're exchanging data between pairs. Once that data exchange is done, you can go to the next step where you exchange data with two different pairs. So what that means, if you're focusing, for example, on process number 1, it can't progress to this next step until it's got its data from process 2. So there's a very simple way to describe this. And so you basically, I was trying to avoid this. You basically, if your first step is sending data to process 2 and receiving data from process 2, second step is sending data to process 3, and you also receive data from process 2. You have a coordinating queue pair where essentially you say the first thing you say, okay, you can send the data to process 2, and then wait until I get the data from process 2. When I've gotten the data from process 2, send the data that's already ready to process 3, and wait until I receive the data from process 3, and I'm done. So very simple way to describe these. Now, this is very similar to what's done in CPU-based algorithms, except in CPU-based algorithms you express it a little differently, usually with exactly the same concept. And it's not surprising that overlap. The ability to overlap computation with collective communication on the network is very, very high. Everything's happening on the card, so why wouldn't you be able to use collective communication? Whereas if you need the CPU to drive the collective communication, the CPU can't progress if the collective can't progress if the CPU is busy doing computation or something else, and so. The big from a application perspective, one of the big advantages of using CoreDirect is the ability to overlap communication and computation. So if you can express your algorithms, the application algorithms, in such a way that can take advantage of this opportunity to overlap, you will have good improvement. You'll have improvement in overall time to solution. The other new piece of support that's been added. Let's see. That's been added in ConnectIB is the ability to support non-contiguous data transfers. Supported by the hardware. So those of you that have have used InfiniBand for a while, you're obviously aware of the fact that even today, anytime you post, send or receive work request, you can post. You use the I/O list, the SGE list, to give. You can use the SGE list to give a description of a non-contiguous region of memory. And so the card already had the ability to do this sort of thing. The way this new capability differs from the still supported, but the previously defined capability is in several ways. One The SGE list that one would use is limited in size to, I think it's 32. You can't go any larger than that. With the new capability, that restriction has been loosened considerably. It's on the order of several thousand. I don't remember the exact number, but you can describe a very large number of non-contiguous regions with a single memory key or a single memory descriptor. The other thing that is different here is there are no alignment requirements in regions. You can give as bad alignment as you want. The hardware will deal with it very well. It really depends on the bus characteristics of your system, not on the HCA characteristics. Probably the most crucial difference here is this memory description involves the new memory description, which we call UMR, and I always forget what UMR stands for because I use UMR all the time. But what it does is it sets up a memory key. And so it's different from the old representation in the sense that anywhere a memory key is used, you can use this non-contiguous data description. That becomes useful, for example, if you want to do an RDMA with gather scatter. That is, if you want to do RDMA from a non-contiguous region to a non-contiguous region. The previous definition, that was impossible, because it wasn't based on memory keys. You could describe either at the send or at the receive, but with an RDMA, either read or write, you have only one. You post only one operation, so you don't do a post on the send and on the receive side. So you could not go from non-contiguous to non-contiguous. And so if you wanted to go from non-contiguous to non-contiguous, you had to have at one end, you had to have the CPU involved to do either packing or unpacking. So with this new definition, the CPU does not need to be involved at all. You set up your memory key and use it. The other thing, the other place where it differs is the ability to is that now there's a support for a much more efficient description of regular structured data. So with so the SGE list is very similar to IOVEX for those of you that are familiar with IOVEX. So for every entry you have to give a pointer and a length. And so if you have, for example, if you're trying to send in a vector every other element or something like that, trying to use an SGE list or something like that is incredibly inefficient. You basically have to have one entry for every one of those elements in your vector that you want to send. At this level, with the current support, the hardware lets you define a regular structure of data, and so you can, with a single entry, you can define the vector. Just like those of you that are familiar with the vector operations in MPI, this maps perfectly onto that. And so you can take, if memory is contiguous in this direction, you can describe this. You can use a single entry in your data to in your description of the memory key to send this non-contiguous data. And even more important than that, you can use a vector of those entries, and you can actually take data from two completely unrelated, non-contiguous data from two completely unrelated memory regions and interleave them. So this, for example, is useful in storage. That's exactly the sort of operations that you would do with some sort of, for example, T10 diff, for those of you that are familiar with storage. I actually do have slides about T10 diff, but I'm almost out of time, so I will not get to them. But this is a very, 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 very nice base technology that's available now. And I'd highly recommend for those that have to deal with non-contiguous data to try this capability, because it really basically is another ingredient in moving processing of network communication to the network, and not requiring the CPU to pack data or unpack data before it gets to the network. So I think I'm basically out of time, so I'm not going to go on to the next topics.
quick question for Rich.
Yes?
So you mentioned 137 million message rates
Yeah.
on the dual core FDR.
That's right.
Okay, so if we take one node with 80 cores
Uh-huh.
and all of the cores are communicating,
Yes.
that will increase the latency. If every core internally are communicating with outside, so how much that will map to the number of message rates? So how much I might need from this 137 if all my cores are communicating with outside with every.
It really depends on how much you need. Depends on the characteristics of the application. So if all the application is if all the application is doing is generating messages, the 137, if I remember correctly, we hit at like 32 processes or something like that. So beyond that, you won't. I mean, the card can't hand. I mean, you won't get any sort of improvement. You know, if your application is also doing computation, and so it's spread out, it's likely that there won't be an issue there. It really depends on the pattern. I don't know if I understood your question correctly.
That's
Yeah.
definitely true. It's just only thinking about it from a synthetic benchmark or from real application that we might hit here. And in this case, with 137, we are hitting this level. That means other competitor with less 4 times, we have a big problem there. That's how I can see it. I mean, whatever the other solution of network, it's 4 times less in message rate, then we would have a bigger problem.
Oh, absolutely, yeah. So this is why. So as I said before, really the message rate is not to say I can push a lot of messages onto the wire fast. You know, because a single core, I don't know of any application that would need this sort of message for a single process. It's really an issue of scale. Yes.